Good morning, everyone. And today, I welcome you all on behalf of Amity University, Amity School of Applied Sciences. So, to just introduce Amity School of Applied Sciences, we have chemistry, mathematics, physics, and environmental sciences. And the courses we offered is a BSc Honors, MSc, and the PhDs as well. So this is the brief profile about the Amity School of Applied Sciences, and so today I will talk on the topic. As you all know, these are the discoveries that stand out profoundly in the decade which started with the year 2010. So we'll travel through the all the discoveries and try to understand what went behind these discoveries. And what are these discoveries, and why these discoveries matter to humanity and as in scientific community as a whole. So the decade have been the most fruitful from the scientific point of view. Why I say fruitful? Because we have found so many things. We have discovered so many things. That we found. There was a Nobel Prize recently given for an exoplanets, and we keep on looking for more and more exoplanets. We discovered many exoplanets in a decade. There were tremendous discovery. There were significant progress in the front of lasers. The lasers got faster and more powerful. It was a significant achievement in the front of the quantum computation, and quantum computing has become a reality. We explored the Pluto using the new Horizon spacecraft, and we know that spacecraft has went beyond Pluto, exploring the space beyond our solar system. Also, what we checked is what we also seen as the spacecraft entering the interplanetary spaces. So we can get more information about the things beyond our own solar system. Well, out of all these discoveries, really stand out from the rest is boson, direct detection of the gravitational waves, first image of a black hole's event horizon. Now, all these discoveries had a history, and it had a mathematical history, because in the nature were given by a theoretical, predicted by a theoretical physicist using a tool which is we call all as a language of a universe, which is mathematics. And of course, and what mathematics have is equations, and all these discoveries basically governed by an equation. So here are the equations which governs the discoveries. So here first is in Lagrangian, which is containing the Higgs, and what you can see here is it's embroidered on the mug, which is basically the souvenir which you get in a Center for European Nuclear Research Laboratory located at Geneva. So usually what we saw for these equations, that we started printing them on the things which we use day to day. So what we have is the Lagrangian containing the Higgs field printed, and then what you have here is an Einstein's field equations, which basically tells you about the relationship between the geometry and the force, that is the gravity and the space-time geometry, and which is printed by Hungary on a stamp, which famously describes the Einstein's field equation, shows the famous Einstein's field equation and the photograph of the genius. Here is Schwarzschild radius, and Schwarzschild radius is basically the radius of predict of an event horizon of a black hole, and we'll describe what this event horizon is. And all these equations what this equation did, this equations basically end up giving a very prestigious, receiving a very prestigious prize, which is a Nobel Prize in Physics. So what happened is that you have seen that these mathematical equations were derived, and this phenomenon were predicted long back, and the Nobel Prize were discovered for the Higgs boson in 2013, and the Nobel Prize for the discovery of the gravitational waves was awarded in 2017 to three physicists, Barry Barish, Kip Thorne, and Rancer Weiss, whereas the Nobel Prize for Physics is given to the Frank Elbert and Peter Higgs. Now you will ask why so much delay. So I will tell you why there is so much delay in the Nobel Prizes. So there is another Nobel Prize which you expect for a discovery, the first ever image of the black hole, which is most likely to be awarded next year. What these discoveries did is this, apart from the excitement in the scientific community, they made an news in a public domain as well. So what you see here is various news agencies take note of this, and there exists a science reporting extensively in the media, and they keep note of these discoveries, where New York Times basically said about physicists find elusive particles seen as a key to the universe. Like BBC says the first ever image of the black hole released, and there is a news in the New York in 1949 with master of the key universe, so forth. So what is the common connection to all these discoveries in the physics? Connection is, of course, the genius named Albert Einstein. So how this connection we can establish? So the Albert Einstein gave a famous theory of special relativity, and which led to a relativistic quantum mechanics, and further developed into the theory of fields, quantum fields, which is called as a quantum field theory. Predict from the theory of quantum field theory is the Higgs boson. Now there is another theory which Einstein published around 1916, which is theory of general relativity. So solution to Einstein's field equation in the general relativity gives rise to the event horizon radius, which is published by the Schwarzschild, which is called as, essentially we know that there exists a object in the universe like the black hole. So to begin with to begin with the black hole, to begin with the discovery of the Higgs boson, what we know is the four fundamental forces in the nature. So what are these four fundamental forces? So as we know that Newton discovered the gravitational force, then there comes an electromagnetism, which is the electricity and magnetism, which basically bounds the atom, and then what you have is the strong force, which plays a significant role in the binding the nuclei, that is proton and neutron together. And then you have a weak nuclear force, which is responsible for the decay of the radioactive particles in the nuclei. And what we have in front of four fundamental forces. In 1970s, what physicists realized is an interesting thing. And what they realize is that there is a connection between the between two of the four fundamental forces. And okay, so let's talk about this connection between the four fundamental forces. So what you have is an electricity and magnetism, and we all know that there is this electricity and magnetism is inseparable, as we all learned in an undergrads, that they together make something called an magnetic theory. And what you have is the force, big force gives rise to something called as weak interactions or weak force. And what is unification of the electromagnetic theory and weak interaction is the electroweak theory. And we all know that what is the force carrier for electromagnetic theory? It is electromagnetic radiation, or what we call as a photon. And what is the force carrier for the weak interactions? So it turns out that there are two force carrier to the weak interactions. What you have is the photon. So electroweak theory have three force carriers: photon, W bosons, and Z boson. Now what we expect is that all these three should be massless, because they represents a theory together with the photon. And what happened is that something happened, and we call this as something called as symmetry breaking, where the photon remain massless, whereas W and Z boson acquired the mass. Now it's basically a surprising thing that photon remain massless and W and Z bosons are massive. Now this come out as a problem in a particle physics, that how I can explain the masses of the remaining two particles of the same theory, that is electroweak theory. Now we also knew that this W and Z bosons have mass nearly 100 times that of the proton, and this mass has been estimated, measured at colliders. Now theorist Robert Brout-Englert and Peter Higgs made a proposal that this problem of mass generation for the W and Z boson can be solved. And what is this solution? This solutions is basically the symmetry breaking in a particle physics. And this is a paper which Englert and Brout wrote in 1964, which titled The Broken Symmetry and the Mass of a Gauge Vector Boson. And there was another paper which Peter Higgs published a couple of months after, and that is The Broken Symmetry and the Mass of the Gauge Boson. This mechanisms gives masses to the W and Z boson, and when they interact with the invisible field, we call now as an Higgs field. Higgs fields actually interact with particles, gives rise to a masses, and that is what that is how the particles are acquire masses. Here it is just an artist illustration of how these particles may drag into the Higgs field. That you can see that the massive particles like electrons or quarks, they have an interaction with Higgs and they acquire masses. Whereas what you see here is the photon. Now photon doesn't have mass, so it is we can very nicely conclude that it doesn't have interaction with the Higgs field directly. Now what we all this study in particle physics about the interaction of the quarks, leptons, and the force carriers, and together with all these particles, fundamental particles, and the force carriers in the particle physics, there comes a Higgs boson, which is responsible for mass generations for all these particles. And what we have now is something called as a standard model with Higgs boson is into it. Now what you have is up, you have a 6 quarks, you have a 6 leptons, you have a force carriers, that is boson, Z boson, photons, and that's graviton, where you can see here that the Higgs boson fits nicely in this picture. Okay, so what are the properties of the Higgs boson? In the standard model, the Higgs boson is an unique part. What makes it unique is it has zero spin, it has no electric charge, and it doesn't have a strong interactions. Means there is something called as an interaction within gluons, where we know that why there is no strong action, because something like something which do not have a mass, it will not have an interaction with that. So essentially the gluons, which are the interacting part, force carrier for the strong interaction, don't have the mass. Now since 1964, the hunt for a Higgs boson began, as predicted by the Englert, Brout, and Peter Higgs, and no detector were able to find a Higgs boson in a detector, and what it leads to the start of the building of the Large Hadron Collider. And what we have is a big, huge machine located in a CERN, Geneva, which is around 27 kilometers in radius, and it has a four detector. Here is actually circulates in this ring, and there are two beams that are interacting at 4 points, and these 4 points are equipped with an detectors which can detect the produced particle. Have is this Large Hadron Collider. So how the ring look like inside the Large Hadron Collider? So ring is typically look like the picture you see here on the left. You can actually take a vehicle and travel across the ring, and that is specifically designed for the maintenance. And there is the cross-sectional view of the ring, where you can see that here there are two beams for the occur. What happens is you have this uh, 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 laboratory where you know that there is an the one of the place where you have the world's highest vacuum and the coldest temperature, and that these all things are required for the experimental purpose. This collision points that we have is a detectors, and this detectors looks like this. So this ATLAS detector is looks like this. What detector? CMS detector, and an LHCb detector. So this, you can see these are the complex structures made up of the detectors to detect photons, leptons, uh, and they essentially gives stored data in the computers, and then what we get is the final result. So typically the collision events which we studied for the Higgs boson discoveries were diphoton event. So what you see here is the diphoton event of collision. You can see that collision point is somewhere here, and there is this beams. Particles are coming out. These are the two photons which are eventually in the detector. That's how we know that the Higgs boson is produced, because Higgs boson produces its decays into the two photons, or then also its decays into the four lepton. See here in the next experiment, the four lepton event, it looks like that. So at a collision point, if Higgs at this point, see here is that there are four lines which basically shows depicting four leptons. So this is just an artistic impression of the how the event will look like. But the reason you cannot see the event by your naked eyes, because it happens at very short amount of time and at very small distance. So this is typically the tracks of the particles, and essentially these particles can be detected, the tracks can be detected. Now all these machines and data gives us something called as an final results, and these are plotted, and these plotted results shows us that in the data, that is events, for example, if you have a photon event, enhancement in the number of enhancement in the number of diphotons. This enhancement is at a mass range of around 225 giga electron volt. And what we can actually infer from this is that we have discovered the Higgs boson, and that is what this uh, says. And these are the papers which is published by the CMS collaborations and the paper published by the ATLAS collaboration, and they shows the observation of the new boson at mass of around 125 GeV, and uh, hence we can conclude that yes, we have finally the Higgs boson. We have discovered the Higgs boson, and it is an integral part of the standard model. Now, one of the interesting thing uh, which I want to emphasize is that what you see here is basically these two papers by Englert, Brout, and Higgs, which are published in 1964. And what we have is a two paper published by an CMS and ATLAS collaboration in 2012. So there's a time frame between the discovery of the Higgs, the proposal of the Higgs and Brout and Englert, and the discovery of the Higgs. There were about 48 years span, and we know that the Peter Higgs and other Brout got a Higgs boson because got a Nobel Prize. The reason is because the Nobel Prize, the science, the physics can be only be believed once it's proven in an experimental way. So that is a remarkable of the one of the remarkable achievement of the decade. Now what we have is the gravitational waves, and gravitational waves is one of the significant theoretical predictions done by uh, uh, Einstein. And what these gravitational waves are, any object which accelerates, means any object, if you apply a force and if it accelerates, it's gives rise to an gravitational waves. Now these waves are basically formed in the in an space time. Now this concept of space time being a manifestation of the gravitation is given by an Einstein, and he said that okay, wait. So he said that if there is a space time which basically have an geometrical uh, uh, existence, then there will be a distortion in this geometry, and that is what gravitational waves are. So when these gravitational waves produces, and it can be detectable gravitational waves, when it can be only produced when there is a huge masses in the universe, they either rotates, it means accelerates, or they collide. So detectable gravitational waves are ripples in this space-time caused by some of the most violent and energetical process in the universe. Okay. So typically, if you have a ripple, this is just an artistic impression that if you have a sheet of the space-time, and if there are two heavy objects are orbiting around each other, they can essentially produce a ripple in the space-time. What Albert Einstein predicted the existence of the gravitational waves in 1916, followed by his general theory of relativity published in 1915. This is the paper published by an Albert Einstein in 1915 for the theory of gravitation, and the paper describing the gravitational waves published in 1916. These papers are written in the German, and during that time Einstein was used to write paper in the German, and later they were translated into English. We have energetic events, and some of the energetic events in the universes are the black hole merger, neutron star merger, or the explosion of the stars like supernova explosion. So what you have is a black hole merger is the two black holes basically and merge to form a single black hole, and it can gives rise to an gravitational waves of huge sizes. Then what you have is a neutron star, which is basically gives rise to uh, gravitational wave. And what also you have is in supernova. There's something huge occurred at the formation of the universe, as we all believe Big Bang must have also gives rise to the gravitational wave. So uh, uh, gravitational wave, indirect discovery of the gravitational waves were done by the Arecibo Radio Observatory in the Puerto Rico. And it's shown that there is a binary pulsar systems that is predicted by the general theory of relativity, which radiates the gravitational waves. But this was actually uh, detecting the system, not the gravitational wave itself. So there was no gravitational wave, direct detection of gravitational wave until September 2015, September 2015. So who made the contribution? So it's the LIGO, which is Large Interferometer Observatory, uh, physically sense the uh, undulations in space-time caused by a gravitational wave generated by two colliding black holes. And these black holes are about 1.3 billion light years away. So what is this laboratory is? So you can see that there are two laboratories around 3,000 kilometers away, and there is uh, you can see here is these two laboratories are operated together by Caltech and MIT. The California Institute of Technology and MIT are both the prominent universities in the United States, and they have built something called these two facilities, and you can see there are some looks like arms located in the large geometric areas. So this interferometers idea were first used by an Michelson-Morley to check the ether hypothesis for the propagation of light, and this is the platform which is built by an Michelson interferometer. So interference is basically an around more than 100-year-old idea which is used by Michelson-Morley, and it has been still used, and it has shown its worth in discovery of the uh, gravitational waves. What you have is two laboratories, two experiment setups. Now we will explain why there are two experiments. So one experiment is LIGO Livingston interferometer, and another is the LIGO Hanford interferometer. So what you can see here is that there is a 4-kilometer long stretch, and what you basically uh, see here is what these arms are about. So these particular arms are basically are uh, light passes through these arms reflected back from the end. So typically the interferometer looks like this. So design of interferometer is you have a mirrors and you have a laser. So laser basically reflect from this mirror, they reflect from this mirror, and this, both waves meet here, and that is how you form the interferometer. Now, what is so interesting about this interferometer is LIGO interferometer are designed to measure the distance, that is 1 by 10,000ths of the width of the proton. So you can imagine the accuracy of the interferometer. So if you have a small change in this, you can actually detect this small displacement in the mirror. So what in fact happens is that uh, uh, once you have a gravitational waves, they are going to change the distance between the one of the arm of the interferometer. So this basically built on the Michelson interferometer that you have a mirrors. Additional to the two usual mirrors, what you have is the Fabry parrot cavities, which are designed to increase the length of the beam. So the LIGO have improved the interferometer with 2 km Fabry-Perot cavities, and then what you have is the they basically include something called as a power recycling mirror as well. So it is basically one of the sophisticated instruments designed with an latest technology and developed technology specifically developed for the detection of the gravitational waves. So what you have is basically you need to figure out much of the noise. So where the noise come from? The noise typically come from the earthquakes or normal, like if your train is passing, you have sound vibrations may cause some and there are so many vibrations exist on the earth, and the task is to minimize these vibrations, and this can be minimized using developing technologies such as, this is a stabilizer which is hanging the mirrors, and what you have is uh, uh, this mirrors suspended these uh, strings, and that's how the strings are made up of silica fibers, and there's so much sophisticated technology go into this. There's also an optics which go into the design of the interferometer. What you have is a LIGO's non-planar ring oscillator, which eventually creates a powerful laser, and then also you have an silica mirror, which they weighs around 40 kg each. And what you have is that you can see here that how this interferometer in fact works. So this interferometer works like if you have a no wave, there will be no shift in the waves, and there will be no shift in the interference pattern. But as the wave is detected, the distance between one of the arm will change, and that is how what you get is the signal in the detector. Okay, and that is what LIGO discovered. So what LIGO have discovered is these two waves, this disturbance in the signal over the usual signal. And what you have is that if you see here, there is an L1 observed and H1 observed. So interferometers simultaneously seen the same disturbance, and I can say that they simultaneously seen the same signal. And what you can see that if you overlap these two signals, see here is that basically overlap nicely, and we can, yes, there is some gravitational wave is detected, and from this particular signal you can infer the distance at which these black holes merge, what is the rotational speed of the merging, and how much time it took from the merge. So you can essentially see that this is the typical analysis where you can see that the initial phase is basically the in spiral that is there uh, uh, spiraling, and when very close to the merger, what you see is very large signal, and essentially then it's just attenuate when they merge into a single object. So this is the LIGO discovery, and with the advancement of the technology and scientific endeavors to search for the gravitational waves, one can say that LIGO discovery will go down in the history as one of the humanity's greatest scientific achievements. Now what you have is a computation and data collection. So when it is observing mode, LIGO generates like terabytes of data every day. These are acquired vast computing infrastructure. For LIGO's first observing run in 2015, the LIGO will be provided 35 million service units, and with worth of computing. Kindly mute your mics, everyone. So what you have is uh, the new proposal to build a LIGO interferometer in India to detect more and more gravitational waves or when any other phenomenon unknown to us. And there is a plan interferometer which is called as an LIGO India. LIGO India is collaboration between the LIGO laboratory operated by Caltech and MIT and Computation is India. One is RRCAT Indore, another is the Institute of Plasma Research Ahmedabad and Ayuka in Pune. So together with these three institutes and MIT and Caltech, India is building a interferometer which eventually will be able to detect the gravitational waves. Okay, now what we have is again that these gravitational waves were predicted by Einstein in 1916. These gravitational waves in 2016, and you know how much it took around 100 years to finally directly detect the gravitational waves. And then in 2017, the physicist, uh, experimental physicist, finally got a Nobel Prize for the discovery of the black hole. Nevertheless, I just want to point out that Einstein's haven't received the Nobel Prize for theory of general relativity. Now there is another uh, significant discovery which generates the curiosity and excited the humankind. And it's basically came in the news. First ever image of the black hole revealed, first ever black hole released, darkness visible. Finally, the astronomers captured the first ever image of a black hole. And you know, we have finally the photograph of a black hole for the first time. And you can see that this looks like, you know, it looks like something, uh, some dark. It looks like basically a donut. You can see that there is some structure with black in the middle, and there is surrounded by it. We'll try to understand what this uh, uh, structure is. So what you have is these are the uh, efforts and scientific collaborations results into the publications in Astrophysical Journal letter in 2019. What you see here are series of paper which gives a scientific uh, mm, details about discovery of the supermassive black holes. So what you have is accretion disk uh, for a black hole. So typically, if you just want to describe the hole, what you have is uh, a structure, and they have various uh, 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 various things which basically goes into the structure of the black hole. So one of the thing is that all we know that the black hole is basically something which is the end state of the star, and it has so huge gravity that nothing escape, even the light can't escape the black hole, and hence we cannot see it. So if we cannot see the black hole, how we can see the black hole and how we can photograph it? So what we can photograph is essentially this we called as an event horizon of the black hole. So what is the event horizon? Event horizon is predicted by theory of relativity, uh, and shortly essentially calculate the radius of the event horizon, and that basically have some perimeter around the black hole, which where even you cannot see the light. And what is there is some interesting phenomenon occurs mm, around this uh, event horizon, where sometimes uh, jets, relativistic jets that emits, because there is something called as an uh, large matter which basically accretes around the black hole, and it results in the of the relativistic jets. So what these jets are made up of? These jets made up of the charged particles and photons, and then photons in all ranges. So what we can actually detect is jets, and these are being detected in Hubble telescope, So this is an image of an Hubble telescope, basically capturing the jets emitted by the black hole. And there is this M87 galaxy, which is captured using X-ray observatory, Chandra, NASA Chandra X-ray observatory. And what we really want to see, and what uh, Event Horizon Telescope really want to see, was this small portion in the M87 galaxy, which is cool. So you need you need to see the black hole. Of course, if you want to see something as far as 13.5 billion lights, 3.5 billion light years away, you need a telescope. But do you need a telescope like this, or do you need a telescope like this? These are typically reflector Newtonian telescopes, which we use for our observations to look at the planets, clusters, galaxies, and save so many other things in the universe. They are just going to tell you the information about the visible universe. Are we going to use the Hubble telescopes, split telescope like the infrared telescope in the space? No, we even don't use this. Can we use the Cake Observatory, which is the one of the biggest telescope till date in the uh, uh, in world? No, because even these telescopes are not capable of capturing the black hole, which is as very small size of around 20 around 40 microseconds. We use the radio telescopes. Well, we can use radio telescope, but even the radio telescope located at one place cannot be used to uh, capture the black hole image. So how we can capture the image? And the requirement is we need scope which is as huge as the diameter of the entire Earth. So this is the telescope looks like of the Event Horizon Telescope. What this telescope is, that this telescope is basically made up of radio telescope located at around six uh, different locations on Earth, from South Pole to African continent to Europe to Hawaii. So you can see that to an South America. So what you see is entire network of telescope is known as the Event Horizon Telescope. Build a telescope, build an array of the telescope. The effective diameter of this telescope will be the diameter of the Earth. So we are successfully able to build a telescope equivalent to the telescope of the diameter of the Earth using this idea of building a large array of the telescope. And what really placed in these telescopes are radio telescopes are placed in each position. We really want to do is we really want to capture the uh, image uh, of the at by capturing the by pointing all these radio telescope at the same uh, direction, that is towards the black hole. And what also we want to do is we want to capture it as simultaneously. So these are the two crucial points. You have to point towards the same direction, and then you basically have to capture it simultaneously. So what we use is very long base interferometry techniques. What this long base interferometry techniques is, so you have suppose three antennas, and if you have a radio signals coming, you actually this and data transmission with an atomic clock. As long as the clock same time, to take just record the data, and that's what Event Horizon Telescope did. And what they used is uh, techniques effectively, and using this technique they created a giant virtual telescope as large as the distance between the two farthest apart telescope stations. So you can imagine the diameter of the telescope is the diameter of the Earth. And that simple technique of very long baseline interferometry is able to create such a huge telescope. Now, what important part is, once you have, what you want to do is, you want to process it. So you need to collect it as well. Now, where these all antennas were pointed towards, they were pointed towards a target, that is the Sagittarius A star, that is a black hole which is in the major object not the Sagittarius A star, but it is an M87 star supermassive black hole. What is the another black hole which is which event horizon people look for? It's a Sagittarius A star, which is in our own. And this is the image on the left hand side of the Sagittarius A star. And what you see in the right hand side is the major object 887, and we need to have to capture the image event horizon of the black hole somewhere lying in this region. So now there is data taking which is done, and as soon as they align the telescope and capture the data, this data were collected in a computer disk, and all these computer disks were essentially brought together. Now what you have also is you need to have a good weather, and this good weather has to be in all these 4 locations. So in April 2017, this data were collected, and there were 4 days were chosen where all the sites were clear. Okay, and what we have is collection of this data. It's single point, and what you do is you process the what you obtain is the image of a black hole. So what you see here is basically the event horizon. So event horizon is an portion in the center that meter surrounded in a donut-like shape inside the meter. And what you see here is basically the radiation emitted by the surrounding region. So since this radiation is in the radio region, this colors not tells you the actual colors of the at the of the accretion disk surrounded by events horizon. So this is not an actual photo of the black hole. Why I say that actual photo of the black hole is basically a photograph which you usually capture using the mobile phone. What this is basically is a constructed image from a data, and this is in the radio region. So yes, so this is the structure of the black hole which is captured using present telescope. What it is a radio image using wavelengths of the radio lights in the radio region. What you see is an image that you see isn't in the visible range, and the same things happens if you want to see an image from an infrared or ultraviolet region. We have to convert these wavelengths to something we see. So that is how this radio image is converted into the something in a color structure. So what we can say is that black hole is not a normal photograph. It is not something you could see if you look through an optical telescope. And these are the images that are published in the paper. So in addition to what you see here in this image, in addition to those published in the newspaper, is that it shows the distance. What is 50 micro? Yes, it is a micro arc second. That is an angular diameter of this object. You can see how much small it is. So 50 microseconds is like the fraction of the seconds. And as we know that 1 degree, you have a 60 minutes. 60 minutes, you have a in 1 minute you have a 60 seconds, and you can imagine that the fraction of seconds how small it is. So what color you see here, it's a bright temperature, and these are the 4 days. So image captured on the April 5th, image captured on the April 6th, and image captured on April 10th, and image captured on April 11th. So what you have is the image of the black holes, which is basically the radius of the event horizon. So Carl Schwarzschild basically have published a paper giving the radius of the event horizon, which is this paper. What we have is from 1916 to 2009, we took almost 103 years to actually see the event horizon of the black hole. That is how the much time the scientific discoveries takes. So, so you can expect that the next Nobel Prize in physics in next year should be announced for the remarkable discovery of the event of the image, that is first ever image of the event horizon of the black hole. So there are so many things about massive black holes, but there is one thing that there are some other black holes, and one of the black hole is in our own Milky Way's galaxy, which is Sagittarius A star, and we will be able to capture the our own black hole. But the problem with the Sagittarius A star black hole is that it is not a relatively active black hole, as active as M87 star. So so I will just try to emphasize the point after going through all these three discoveries, that is then elusive particle, Higgs boson, to gravitational waves, which we cannot, which are very hard to detect, and the black hole, which basically, it's one of the mysterious object in the universe. And it took a large effort of the large number of people, collaborations, they come together, build a collaboration, build a huge facility, huge funding, huge experimental facilities. And that is how they made, that large number of people together made a contribution to the progress of the science. And this is how the science have made progress over the years. So there is a clear path laid out to continued exploration of the universe. And all it relies on is extending what we are already doing. So it's important that we keep doing a scientific exploration. And we do not know what secrets nature holds beyond the already explored frontiers. But we do know one thing for certain, and that is, if we don't look, we will never learn. So we have to keep looking for an unknown, and we have to keep learning. And I will leave you with a photograph which I recently captured from a mobile phone. And now you can see that technologies enable us to see, and this is the photograph showing the Milky Way. And I will end up with a note that we'll keep finding the mysteries of the universe, and we'll keep shining like these stars. And thank you for listening to the talk.